All right, welcome to eCampus. Today we are going to attempt a rather recent past paper. This one is from May-June 2024, Cambridge IGCSE Physics Paper, paper 3 particularly, and this one is variant number 33. As with all papers, the question paper starts with instruction, which is imperative that you have a close look at. This is our session. We might not be looking into it in great details, but you should have a look at it. This will give you key information about what to use and how to answer questions, the details about constants, etc. So let's start with question number one. So a girl is cycling along a straight horizontal road, and this is a figure one. It shows the direction of forces acting on the cyclist as she cycles in the direction of force C. So it's given that she's moving in the rightward direction. So state which forces show the direction of the force of gravity. So force of gravity is a simple one. Force of gravity acts in the vertically downward direction. We know that because the gravity is a force which pulls everything toward the center of the earth or center of the massive object. So force D is the force due to gravity. We know that it was an easy one. The force due to air resistance. So it is quite obvious that when you are moving in the rightward direction, the force due to air resistance would be the one opposing it. And so force A would be the force due to air resistance, right? As she's moving rightwards, and we have been given four forces. Out of these four, force A is the force due to air resistance. Okay, now third one, force A changes and become larger than the force C. State any effect this change can have on the motion of the cyclist. So we need to think it in a different perspective. When force A becomes greater than force C, that means the net force would now be acting in the leftward direction. So net force would be acting in the leftward direction. That means that the cycle will start to decelerate, that the bicycle or the rider would start to decelerate, eventually reaching zero velocity and then starts to increase velocity in the leftward direction if force A still be greater than force C. So any effect this change can have on the motion of cyclist is that she will experience deceleration. Or we can also say that her velocity will decrease. They mean the same thing. You can mention either of them. Moving on, another cyclist travels a distance of 250 meters in a time of 21 seconds, and we have to calculate the average speed of the cyclist. It is again an easy one. We know that the average speed, we can mention it as average, is equal to the total distance covered in the total time which is being averaged. So 250 meters is the distance covered divided by 21, which will give us, let me quickly open the calculator, which you should have right beside you in the examination. So it's 11.9 meter per second. So that's it. I think that's question number one. Oh no, we have one more part. Part two. Now the cyclist exert a force of 36 Newton to move the cycle forwards. So 36 Newton is the force applied by the cyclist to move forward. That is, we can assume any direction, rightward or leftward. So calculate the work done by this force when the cyclist travels 250 meters. And we have to also tell the unit. So remember the definition of work done. Work done is force applied in the direction of motion. Work done is F, which is a force, multiply the distance covered in the direction of motion. So we know that when the force of 336 newtons applied by the cyclist, the distance covered is in the direction of force. So we just need to multiply the two things together. 36 multiplied by 250, which will give us 9,000 Newton meter. We can mention any unit. So we can simply write work done is 9,000. And the units we can either mention joules or we can mention Newton meters. Yeah, that's it. So, all right, let's move to question number 2. So we have been given figure 2.1 and it shows a road sign on the ground. So this is a front view, we have a base and it's placed on the ground, and we have a side view as well. So a strong wind blows and the sign begins to fall. A man catches the sign before it falls completely. So figure 2.2 shows the force applied to the sign by the man. So what is the question? Calculate the moment of the force 5.6 Newton which was applied by the man about the pivot, which is also shown here, and we have to been given information figure 2.2. We need to find the moment about this pivot point P. So now we know the moment of a force is equal to force multiplied by the perpendicular distance between the line of action of force, which is this one, and the pivot point. This distance is given to us, right? This is the perpendicular distance. It's 32 centimeters given to us, and force is also given to us. We simply multiply the two quantities, which is 5.6 multiplied by 82. We don't need to convert it into meters because the answer is already given in Newton centimeter. We need to present the answer in Newton centimeters. So we need to be cautious about that as well. So what is 5.6 times 82? 459.2 Newton centimeter. So this is the moment of a force, 5.6 Newton force about the pivot as shown in figure 2.2. The sign needs to be easy to move and stable. The base cannot be fixed to the ground. Suggest how to change the base so that the sign is more stable. Explain your answer. So we need to give a suggestion about how we can make the signboard more stable, and we need to give an explanation as well. So one thing, as we all know, that if we can somehow lower the center of mass of an object, it will become more and more stable. How we can do that? One good suggestion would be to increase the mass of the base. Another could be to increase the size or the area. Both will do the same thing. Both will increase the mass distribution in the lower portion and will eventually increase the center of lower down the center of mass of the signboard. This will, we can simply mention that this doing this will lower the center of mass of signboard. That's it. Moving on to question number 3. So this is a hydroelectric power station transmitting electrical energy to homes and factories. We have a reservoir, which is shown as the water behind dam. Then pipeline, it drives the turbine of a hydroelectric power station, and the generation generates the electrical power, and which is transmitted over cables, distribution transformer, then powers homes and factories. State the energy stored for the water behind the dam. So water behind the dam, uh, the energy source is the potential energy or the gravitational energy. All right, so in the list of equipment, draw a ring around each item that a hydroelectric power station requires. We have been given some usual components in a we have been given some usual components of a power station like boiler, cooling tower, generator, solar cell, turbine. We have to specify which of these components are installed or you may find inside a hydroelectric power station. So boiler is used to increase the temperature of water temperature inside a closed loop system. We don't need that in a hydroelectric power station. In a hydroelectric power station, simply water from a high potential drops down on a turbine which rotates the shaft and generates electricity. So boiler isn't needed, neither is a cooling tower. We do need the generator and we also need the turbine. We don't need solar cells. Solar cell is an indigenous power source. It's renewable energy, but we don't need in a hydroelectric power station. State the type of transformer shown in figure 3.1. So we have studied step up and step down transformers. We know that when the electricity is transmitted over transmission lines, it's at very high voltage, 220 kV or 500 kV. And this varies in different countries, but it says that it is high voltage. So when it is delivered to our households or factories, it is step down. So the transformer, which is shown adjacent to the homes and factories, should be a step down transformer. Give two reasons why the power station uses high voltage to transmit electrical energy over long distances. As I just said, that power transmission is done at high voltages. Why? Why it is done at high voltages? So when you step up the voltage, because the power remains the same, the current in the secondary side or the transmitted side drops down. So lower currents in wire and hence lower power dissipation. That means the I square R losses would be very low. Secondly, the size of conductor would also be small because lower currents have to be transmitted over long distances. So that's two reasons. Sufficient enough. Moving forward, hydroelectric power station may replace coal-fired power station. This is a good one. State two advantages and two disadvantages of using hydroelectric power stations compared with coal-fired power stations and do not include building or maintenance costs. So we have to give some technical answers to this. Let's start with advantages. The one of the very big advantages that they currently hydroelectric power stations are hailed worldwide, and uh, we hear of sanctions, we hear of reducing the carbon footprint. Is that coal-fired power plants have a very big carbon footprint. They add to the global warming carbon footprints and deteriorate environment. Okay, that's one advantage of using hydroelectric power plants because the coal-fired power plants have carbon footprints. Okay, so what is the other advantage of coal-fired of hydroelectric power station? They don't use any fuel. No fuel require mean no fuel run cost because the water is the only water at higher potential is used to drive the shafts. So in a hydroelectric power station, no fuel is required, which in other cases like gas fired or coal fired or even nuclear power plants, fuel is required. What are the disadvantages then? Disadvantage, one big disadvantage of a hydroelectric power station is that a huge area is occupied as reservoir. And it basically damages the habitat, the local habitat of animals and flora. Another disadvantage of a hydroelectric power station is that it is dependent on the upstream water sources, on the provision of water actually. So as the water in summer season, normally we have heard that in summer season when a lot of ice melts, the reservoirs are full and they are running at full capacity. In the winter seasons, when the melting rate drops down, obviously, and the water in the reservoirs fall below a significant level, and we see lower energy being produced over time. So it is dependent on provision of water in some cases, and normally in the uphill areas. In winter season, these hydroelectric power plants normally completely dry out and they do not generate any energy. So that's it for advantages and disadvantages. And I think that's question number three. Yeah. All right, moving on. Let's have a look at question number four. So figure 4.1 represents the arrangement of particles in a solid. We can see here. Describe the motion of particles in a solid. So motion of particles in a solid is vibratory in nature. That means they don't have the kinetic energy. They're only vibrating at their um, very own self place. So vibrating motion would suffice. On figure 2, draw at least 10 particles to show the arrangement of the particle in the gas. So we need to draw a container for the gas. We know that the gas particles are scattered, random, and randomly moving, and they don't have any, they often collide with each other as well. So we just display 10 or more particles in arbitrary fashion. I think that will suffice. Describe the motion of particle in the gas. Random motion, scattered, and high kinetic energy, and low electrostatic forces. We can mention any of the two to get our marks. Moving on, part B. At the beginning of lesson, students measure the mass of water in a shallow dish. Shallow is an important word because shallow dish has a high or a larger surface area. Figure 4.3, mass of water at the beginning of lesson, this one. And at the end of session, we see a significant drop of 25 grams. State the name of the process that decreases the mass of water in shallow dish. It's not boiling because this thing is placed at room temperature and students are measuring it and there is no energy source as well. So this must be evaporation. And the shallow word also gives it away. So the process is evaporation. All right, describe the process that decreases the mass of water in the shallow dish. So we have to describe evaporation as well. So the process in which liquid, we can also say water, is converted into gaseous, to gas. It occurs at all temperatures actually, and happens at the surface. So we know when the molecules or particles present near the surface, they gain sufficient energy, they migrate or they transfer into the gaseous state. So it always occurs at the surface. So that's why it's mentioned shallow dish. If this were more shallower or the surface area was even more, the number of grams reduced would be even larger, and vice versa as well. Question number 5. Figure 5.1 represents an arrangement for heating water. Hot water is stored in the metal container as well. So there's a heater, cold water flows in from the bottom, and hot exits from the top. Explain why the hot water is available at the top of container and use idea about density. Well, they have given the answer in the question. We know that when water heats up, it expands, and hence its density decreases. When the density decreases, lower density objects, or we can say objects or lower density items, tends to float atop the higher density ones. We've seen that countless times. And also, this is the process of convection. This is convection, right? So I think that's enough. The electric heater is switched on for 1 hour every morning. State the name of process that transfers thermal energy through the wall of metal container. Now, the through the wall thing is very important because if that's not given, then there are a lot of ways where thermal energy can be transferred, like radiation, where thermal energy can be radiated in the form of electromagnetic waves, in not requiring even the medium. But here it's mentioned that this is through the walls, so this is conduction. So just one way of keeping the water hot after the heater is switched off. Yes. So the easiest one, with the first thing that comes to mind is use an insulation. Insulation on, or in fact over the container, and the insulation can be plastic sheet or any porous or any non-conductive material. That's it. That's question 5, I think. Yeah. Let's go into question number 6. State the name of wave in which the direction of vibration is at right angles to the direction of travel. So this one is the transverse waves. I want you to imagine the example that we did uh, in our revision session, in our even classes as well, where a man using a long spring or a sling would move his hand up and down, and the wave is created like this. This is the example of transverse waves. Moving on to 6b, a teacher uses a ripple tank to demonstrate a wave property. All right, these wave crests pass through the aperture and the wave is bending. Complete the sentence about the wave property. The wave property demonstrated is it's not reflection, neither it is refraction, because the medium is not changing. It's not dispersing. It is diffraction. Why it is diffraction? Because diffraction involves the bending of wave when it's passed through a significantly low aperture size. So this is diffraction. On figure 6.1, indicate one wavelength. So wavelength is the distance between two consecutive crusts or troughs. We have been highlighted there. So this is one wavelength. In a different ripple tank, the wavelength of the wave is 5.1 centimeter given, and the wave speed is this thing. So this thing is the lambda, and this thing is the v, which is the v speed. We will use the wave equation, which is v is equal to f lambda. So f is equal to v over lambda, which is 42 over 5.1. The answer would be 8.23 hertz. That's it. Moving on to question number 7. Figure 7.1 shows a ray of red light incident on a glass prism at point P, and the ray of red light is refracted at point P. That means it moves from one medium to another, that is from air to glass. That's the definition of refraction. For a 1 mark question, we have to draw the normal at point P. We know that when we are drawing normal, we draw a perpendicular to the impact surface, which happens to be the glass surface here. So let me attempt to draw. Yeah, this should give us 1 mark. In paper, it is recommended that you use a ruler to draw it perfectly straight and more readable thing. Okay, so draw the path of ray of red light through the glass prism and into the air. It's a 2-mark question. So the ray of red light refracts from air into the glass and then from glass into the air. So we need to draw the path of this light as it refracts from one medium to another. Before attempting to draw the line, let us quickly recall the concept of refractive indices. So refractive index is a property of a material, and we know that the refractive index of glass is more than air. So when a refractive index of a material is larger, it happens that the speed of light in that particular medium happens to be slower than the speed of light in vacuum or in a medium with lower refractive index. So glass with a refractive index larger than the refractive index of air, the speed of light should be reduced in that particular medium. And also when the refractive index is lower, the light bends towards the normal. And when the refractive index of the oncoming or the where the light is entering into the newer medium, if the refractive index is larger, the light speeds up and it moves away from the normal. So based on these quick concepts, and as we recall, we try to draw the line here. So I'm going to use a different color just for the understanding. Let us draw the line, extend the line as it were moving in the same medium. Okay, so since the glass has a refractive index more than the air, the speed of light should be lower and it should move towards the normal, which happens to be this blue line. So let me draw the path of red light in the glass. So this one. Okay, so this is the path of red light in the glass when it enters from air. Okay, so the light will keep on traveling in this straight line until it meets the other boundary. And again, we will draw the normal here. And again, let me quickly extend this line. And since now the light is entering from glass into the air, which happens to be a medium of low refractive index, the light will speed up and it will move away from the normal. So let me quickly draw it again. So this is the normal here, this one, it will move away from the normal. So this is again an indication. Okay. And just for a quick recall or just for a quick revision, the angle of reflection or the angle of refraction is the angle from normal. Yeah, this is the angle of refraction. Similarly, this is the angle of refraction. This is just for the revision purposes. Okay, so that's it. I think this should give us 2 marks. So as it enters from air to glass, the refractive index is higher, so it moves towards normal, and it moves away from the normal in the second part when the ray of light enters air from glass. Okay, moving forwards, let's move to part B. Okay, a ray of blue light replaces a ray of red light. Okay, the angle of incidence for the blue light entering the prism is the same as in figure 7.1. Describe any difference between the path of the blue ray in the prism. So they've just replaced the ray of red light with the ray of blue light. Everything else remains the same. And we need to explain the differences between the path of the blue ray in the prism and the path of red ray in the prism. Also, this is a 1-mark question. So what's the difference between a red light and blue light? So if we can remember the electromagnetic spectrum, the blue light is on the right side of the spectrum where the wavelengths are lower or the energy is high or the frequencies are high. So when the wavelengths are lower, we say that wave speed will be lower, and that means that refractive index of blue light in the glass obviously would be higher. So we can say that there will be more refraction, or we can also say that the angle of refraction would be lower. So we can simply answer that there will be more refraction Uh, and we can also say that there will be lower angle of refraction. That should give us 1 mark. However, for the sake of understanding, we can also let me also show you how it will look like if we were to draw that here as well. So imagine this was the ray of blue light. So when this would enter into the glass, it should have a lower angle of refraction. So this thing was the previous angle of refraction. It would be something like this. This would be slightly shorter angle of refraction. So that means the ray of blue light, everything else remains the same. The ray of blue light would refract more compared to the ray of red light. All right, moving forward. Another ray enters a glass prism and is totally internally reflected. State two conditions for a ray to be totally internally reflected. If we recall our lessons from chapter number 3 and 4, there were some conditions about how this total internal reflection can be achieved. So the first condition was that the angle of incidence must be greater than the critical angle. Uh, the critical angle, let me quickly change back to blue. The critical angle was a material specific property, and we say that if the incident angle is greater than the critical angle. Yeah, that's one condition. Here for a given substance. And what was the second condition? The second condition was that the incident ray should be moving or should be entering the medium of lower refractive index. That means that, for example, the ray of light or the ray of light should be entering from glass into the air or any other combination of refractive indices. Not the, for example, if the ray of light is entering air from air into the glass, you cannot have total internal reflection. Both of these conditions should be met in order to observe total internal reflection. All right. Moving forward, I think that's it for question number 7. Yeah. Let's move on to question number 8. Figure 8.1 shows part of a circuit for measuring the resistance of a lamp. Yeah, figure 8.1, we can see that there is a battery here. Uh, we have an ammeter. We have an ammeter which is placed in series, and then we have a lamp. What we need to do, draw a figure 8.1. Draw on figure 8.1 to show how to connect a voltmeter to measure the potential difference across the lamp. Use the electrical symbol for the voltmeter. So 2 mark question. We remember the symbol of voltmeter, but however, first of all, the voltmeter is always connected in the parallel to measure the potential difference across the load. So this is the symbol for the voltmeter. We also need to measure the polarity. Yeah, this is positive, this is negative. So as it is placed in parallel, this side would be positive. Okay, the current in the lamp is 0.41 and the potential difference across the lamp is 12 volts. Calculate the resistance of the lamp. It's a very easy 3 mark question. We will use simple Ohm's law, which states V is equal to IR, or we can also write R is equal to V over I. We know the potential difference across the lamp, which is given as 12 volts. Also, the current through the lamp is also given, that is 0.41. We need to give the resistance of the lamp, which is 29.27 or 29.3. Yeah. Moving forwards, calculate the electrical power transferred in the lamp. Okay, so we can use any formula for power, electrical power. P is equal to I square R or P is equal to VI. The answer would be the same. Let's use P is equal to V, that is potential difference across the lamp, times the current through the lamp. We are given 12 multiplied by 0.41, which is equal to 4.92. 4.92, and we have to tell the unit as well, that's watts. All right, moving on to question number 9. 9a, figure 9.1 shows three devices: a compass, a transformer, and an electromagnet. The main parts of the devices are labeled, like a compass needle of a compass, the transformer cores and coils, and the electromagnetic core. So we have to complete a table, the table 9.1, by adding a suitable metal for each part and choose from the metals in the list. So we have been given some metals, and like aluminum, copper, soft iron, silver, and steel. And the catch is each metal can be used once, more than once, and or not at all. So we just don't need to do any retrofitting here. We just need to be rational here while answering this question. So let's start with the compass needle. Uh, Compass needle is a ferromagnetic material as it reads the magnetic field of the earth. So it should be a ferromagnetic material. However, we also have soft iron and steel both here. Both are ferromagnetic. However, the soft iron needs to be magnetized. Its hysteresis loop is very narrow. That means that it needs to magnetize or demagnetize again and again as the voltages across it are dropped. That's why it's not suitable for a compass needle where the magnetization and demagnetization cannot be done on the go. So we need a material whose magnetizing ability is permanent or long term. So we should be going with steel. Steel is a ferromagnetic material and it retains the magnetization in long term. Okay, I'm going to deal the transformer core and electromagnetic core collectively. Both are similar in the sense that the wire is wound around them, and they support the permeability as well, and enhances the permeability as well. So the material choice would be something that it should be a ferromagnetic material, and the choice should be exactly opposite as we made in the compass needle one. So it should be a material whose magnetic field or magnetization ability um, removes or diminishes instantly as the voltage across them is removed. Otherwise, it would not be an electromagnet or a transformer. For example, if I turn on the voltage, it becomes an electromagnet. And as soon as I remove the voltage, the magnet stops working. So it should be a material that only retains the power as voltage is applied across it. Same goes for the transformer. So it should be soft iron because soft iron possesses the requisite properties. About transformer coils, as we know, the choice of coils should be something that has lower resistance. Copper has very low resistance. Silver has very low resistance, but silver is very expensive compared to copper. So I'm going to go with copper. Okay, moving forward. Part B, the primary coil of a transformer is connected to a main supply of 220 volt AC. It's good to write the givens as this is a question involving the formula for turns ratio. The primary coil has 1500 turns and the secondary coil has 650 turns. So the formula was Ns over Np is equal to Vs over Vp. That is number of turns on the secondary side, number of turns on the primary side, voltage on the secondary side, and the voltage on the primary side. We need to find Vs. So Vs is equal to Ns times Vp over Np, which is voltage as secondary voltage. Number of turns on the secondary side is 650. Primary voltage is 220, and number of turns on the primary side is 1500. Putting that in the calculators, 650 multiplied by 220 divided by 1500. So 95.3. I can say 95 volts up to the two significant figures. All right, question number 10. The nuclide notation for an atom of protactinium 234 is this one. State the number of protons in an atom of protactinium and the state number of nucleons in the atom protactinium. Okay, we know that the number of protons obviously is a lower one. Is also mentioned on the bottom side. So 91 is the proton number, and the nucleon number, being the sum of the neutron and the proton, is the higher one. So number of nucleons is 234. Three forms of the element protactinium are protactinium 234, 230, 233. State the name given to these different forms of the same element. Yeah, same proton number but different nucleon number. That's isotopes for you. It's again an easy one. Okay, part 3. A teacher demonstrates radioactive decay by using a sample of protactinium 234M. M stands for the metastable state. That's not the question here. The sample emits beta particles. State the nature of a beta particle. So beta particle is a high energy particle. High energy particle. It can be electron. In that case, it will be called beta minus, or positron. In that case, it will be called beta plus. And it's depending on the positron or electron. Obviously, positron has a positive charge, electron has a negative charge, uh, and it's at high kinetic energy. That's enough for question number 1. We can even mention one or two of them to get the 1 marks. Okay, part 2. The teacher obtains data for a decay curve. Figure 10.1 shows a decay curve for the sample of protactinium 234M. On the y-axis is the count rate, counts per second, and the horizontal axis is time. Calculate the half-life of protactinium using the information in figure 10.1. Clearly show you're working on the graph or in the space provided. Okay, so when solving this kind of question, let me see how much marks this question has. Yeah, 3 marks. So we have to show sufficient working. Let's first of all write the legends, or say the what one block, a vertical block, is worth. So one y axis block is like 20 counts, and one x-axis block is 10 seconds. Okay, so now we need to calculate the half-life. Half-life is determined or is defined as the time when the counts or the individual atoms of the original samples drops to half. So we've been given count rate. It was 900 at time t0. We need to find the time when 900 drops to 450. So this is 900. We know that this thing is 20, so 20, 20, 40, it's middle of these two things. So here, okay. If we just go down here, you can use a ruler to be more precise, and paper again. It's something right here. So one block was, remember, 10. So it is something around 68. I'm going to write 68 seconds. Again, your working would be much better if you use a calculator. So you can, sorry, if you use a ruler. You can also draw some vertical line with pencils to be more exact and show more working. So I'm going to write 68 seconds. That's the half-life. Okay, so just the reason why the half-life of protactinium makes it suitable for this demonstration in our lesson. Okay, we know that half-lives of different elements varies. It can be as low as like picoseconds or nanoseconds, and it can go as long as billions of years. So the choice of protactinium for demonstration in a class, it's a lesson is usually 50 to 60 minutes. So this makes it a perfect element for demonstration purposes at as number of requisite half lives can be spent, and you can see the requisite results in a class. So it's not too short or neither too long to be to experience decay in a class. So that's it. Moving on to the last question, I think. Yeah, this is the last one. Question number 11. 11A states that the solar system contains a number of objects. Some of these objects are listed, like asteroids, planets, the moon, and the sun. This is the solar system, our very own solar system. Write these objects in the order of their sizes. Uh, uh, just remember that this is solar system here. In any other star system, we cannot be too sure of the sizes of the asteroids, but here we are pretty sure about the sizes of moons, etc. So if we're gonna arrange them in the ascending order, so smallest would be asteroids, then come the moon. The moon's our moon, obviously, and then planets, because it's the moon. We need to be very selective, and then the sun. Okay, 11b. Redshift is an increase in the observed wavelength of the light emitted from distant galaxies. Okay, state what redshift indicates about the movement of distant galaxies. So, if a galaxy is redshifted, that means that that particular galaxy is moving away from us, or it is receding, moving away from us. Like we are all moving in an outward expanding direction. And doing so, that particular galaxy or whatever thing is redshifted from us, that is moving even farther away at the speed greater than the speed of our speed outwards. For example, this is the center of the universe, hypothetical center of the universe. It's the Earth here, or the solar system, or any, or our galaxy, whatever thing. For example, this is Earth here. It's moving in this direction. I'm just giving you a hypothetical object. Let's this moving at 10 units per second, and that galaxy is also here. It's also moving there, but this is moving at 20 units per second. That means that this thing is red shifting from it. It's moving away from us at a higher rate. If this is also moving at 10 units per second, then that means that obviously we are relatively stationary. And if the speed is lower than 10 units per second, then it would be blue shifted, or it's moving closer towards us. Okay, moving forward. State by redshift in the light of from distant galaxies supports the Big Bang theory. Okay, the Big Bang theory states, I'm going to write this besides as well. Big Bang theory states that the universe is expanding. And the redshifting of distance object basically proves it or supplements it, as it also indicates that the universe is expanding. We also write let me also write that the red shifting and the red shift supports it. So moving on to part C, it says define one light year. So one light year is the distance traveled by light in vacuum. That means 3 times 10 to the power 8 meter per second uh, in 1 year. So it is distance traveled by light in 1 year. Remember that I said one in vacuum. We know that the speed of light varies in the depending on the medium that that light is traveling in. So it's the speed at which the light travels in vacuum. So it is 3 times 10 to the power 8 meters per second, approximately. So part 2 says that scientists can send spacecrafts to planets. There are many planets outside the solar system. There's just one reason, other than the cost, why scientists do not send spacecraft to planets outside the solar system. So we cannot talk about the cost. One of the very pivotal reasons why there hasn't been a mission to another planet outside solar system is that the scale of the distances in the universe is so gigantic that the nearest solar system to our solar system is Alpha Centauri, which is about 4 to 5 light years away. That says that if we travel at the speed of light, it would take us 4 to 5 years, and we are nowhere close to traveling at the speed of light for now. So the distances between the planets outside solar system is too large. All right, final one. An electromagnetic wave travels from sun to the earth in a time of 500 seconds, and the speed of the wave in space is 3 times 10 to the power 8 meter per second. Calculate the distance traveled and calculate distance between the sun and the earth. Okay, so it's a very simple question. So distance is speed over multiplied by time. So it's 3 times 10 to the power 8 multiplied by 500. We need to give it the answer in meters, so we just need to multiply the two quantities together. Let me quickly do that in the calculator. 3 times 10 to the power 8 multiplied by 500. It's 1.5 times 10 to the power 11 meters. That's it. And that's the end of the paper. We will be solving similar recent papers from Edexcel and Cambridge in days to come. So if you like the video and want to see similar papers, subscribe to our channel. Thank you so much.